Hello again. So in today's lesson, we're working on chapter 4 about light and telescopes. But this is a continuation of our Exploring the Sky unit. And our what are we summary is we are curious. Which is a very noble trait. We are very curious and we like to study and gather knowledge about our universe, about our surroundings. And so how we do that is by some of these tools that we use. And in astronomy, astronomers are very interested in gathering all the light that they can from a celestial object. And this one takes a look at what we can learn from that. So this is a nice one to get us started. So chapter 4 for us. Okay, so light is a treasure. It links us to the sky. And this is a huge telescope. So there's actually a little person right there, and this is a huge telescope. But it helps us to gather the light and to focus it so we can create that image and see what we can see. To gather light with visible light, a small telescope would suffice, and that would work fine. If we think back to what Galileo was able to accomplish with his just rudimentary telescope, taking a look at the moon, Jupiter, and its moons that orbit it, the Galilean moons. So that could work just fine. But if you recall, visible light is just a tiny portion of all the electromagnetic spectrum. And so astronomers are interested in taking advantage of all manner of wavelengths of the electromagnetic radiation. So it's not just that they're going to map the constellations and the phases of the moons, that's all good, but needing these sophisticated instruments and techniques to investigate, we want to find out about the composition. So what elements and compounds are in our celestial objects, the motions, so their speeds, their directions as well. Are they coming toward or away from the Earth? The internal processes. And so in our star unit, we'll see how these tools help us to understand what is exactly going on inside. So internal processes, and of course evolution of celestial objects. So we'll be kind of taking a look at that when we look at the universe as a whole, so how important this is. So we want to learn and start by looking at the nature of light. Undoubtedly you've probably seen, a little soap bubble and all the iridescent kind of colors in that, or perhaps a rainbow kind of thing. But yeah, light can behave as a wave, but it can also behave as a particle, so a little photon or a packet of energy. I like to liken a photon to. So yes, a combination of electric and these magnetic kind of waves can travel completely through empty space. It doesn't need a medium, like say for sound, we need a medium to kind of carry that, so like a solid, liquid, or gas. But in space, electromagnetic radiation doesn't require any sort of medium, so it could travel through a vacuum in that sense. So yes, made up of both electric and magnetic aspects of it, that we end up calling that the electromagnetic spectrum, the radiation. And radiation means that it just radiates out in all directions. And so if we're looking and thinking about these electromagnetic radiation waves, we do think about the wavelength. So, an undulating kind of wavelength. And so from one peak to the next peak of a wave, draw a little wave like this. Okay, so from here to here, we call that a wavelength. And there are various wavelengths. We abbreviate that with a little lambda Greek letter there, so we'll probably use that a lot. But yeah, that distance between the peaks is known as a wavelength, and travel through space at 300,000 kilometers per second, or if you want that in miles per second, 186,000 miles per second. And this is all manner of wavelengths of the electromagnetic spectrum. We think of the speed of light, and we think of visible light, but it's all manner of the electromagnetic spectrum. So that is the speed of light. All electromagnetic radiation travels at that speed. And so the spectrum, as the light kind of gets divided up, we can look here at the visible light portion of our electromagnetic radiation. And so we think about them according to their wavelengths, but so colors of the visible light have different wavelengths. Reds would have the longest wavelengths down towards this end, and they're using nanometers in here, okay, for that. Or if you needed it in meters, you know, you do your little scientific notation for that, because it has lots of zeros on it in there, 0.0000 to the -7 there. But nanometers is a pretty good unit for this. Angstrom is another good unit when these are those small numbers that I talked about, scale from the very first chapter that we looked at. But the reds, the oranges, and then the reds would have the longest wavelengths on this end, and the shorter wavelengths down here. The blues and the violets, the indigos kind of down on the other end. So these would be the short wavelengths, violet having the shortest. So on the order of near 400 nanometers. So a spectrum where the visible light, as you put that through a prism, it will spread out the light because of the bending of the light. So if you think of a rainbow, the light's coming through the raindrops in the atmosphere and getting spread out into a spectrum. So the electromagnetic spectrum is what we call that. And you do want to get familiar here with which wavelengths kind of are the shorter end of the spectrum versus which are the longer end of the entire spectrum. I think that's a bullet on your study guide. But here, like I was mentioning, these are some good units for very small measurements. The nanometer, so 1/1000th of a meter. That billionth in there is a 9. So this is 10 to the -9 meters. Or also, a lot of times they use the angstrom, which is 10 to the -10 of a meter, or 0.1 nanometers, because that's -10 and this is -9. So these are some good units that we use for very small measurements. Okay, remember how scale, we do change up our units according to what it is that we're measuring in astronomy. And then, so here's our whole spectrum. The gamma rays are on the shortest end of wavelengths, and then the X-rays and the ultraviolet. And here's our little window of the visual, okay, and they kind of spread it out here and enlarged that, but that's just a small part of the spectrum. That is what our eyes have adapted and evolved to be able to take advantage of here on the planet. So that's kind of what we think of as light, okay? And then the infrared, so kind of near the red part, but infrared. We cannot see infrared with our eyes. Then the microwaves, longer still. And then you start to get out here into the radio waves. So FM and AM radio waves. And we do take advantage of the radio waves in trying to study the universe as well. So that's your whole spectrum. You do want to make sure that you know which ones are longer, which ones are shorter. Here they're talking about the UV. Okay, there's they're shorter than the violet end. So they're just ultraviolet. So here's our visible end, getting to about 400 nanometers, and then the ultraviolet. We can't see ultraviolet light either. We just see the visible spectrum with our eyes. Okay. Then your X-rays are shorter still than even your UV, and then your gamma ray. Those are the shortest of all. Okay, so do know kind of your hierarchy of your electromagnetic spectrum, what's longer and what's shorter, sort of thing. Okay, and I mentioned the photon, that light, yes, does act like a wave, but it also behaves like a particle, or what we call this little photon, a particle of light, a little packet of light that carries energy. And the way it carries energy, or how much energy it carries, is related to its wavelength, and it's related in an inversely proportional manner. We did mention the inverse kind of square relation when we talked about Newton's law, how that was inversely proportional. This is another inversely proportional relationship. So the shorter wavelength photons carry more energy, so inversely proportional to the wavelength. So the violets and the blue end of that visible light spectrum, let's say, very short wavelengths, those are going to carry more energy than on the other end of the visible light spectrum, the red wavelengths. Okay, those are longer. So the longer wavelengths, say like a red end of the visible light, those are going to carry less energy. So it is an inversely proportional relationship to the wavelength. Okay, so the shorter the wavelength, like a blue, would carry greater energy, and a longer wavelength, like the red, would carry less energy. So inversely proportional. So, and that's just kind of visible with the red and the blue there. But X-ray photons are going to carry a lot more energy. Remember how the X-rays are just underneath the gamma rays. Gamma rays would carry even more. So going clear to the other side then, a radio wave or photon would carry even less energy. Okay, so the longer those wavelengths get, the less energy they carry. So they're interested in, all manner of electromagnetic radiation, because that's how we can learn anything about these celestial objects. We need the light from it. So planets, stars, and the other celestial objects, we rely on the entire electromagnetic spectrum to learn about the universe. Okay, and so on Earth, we do have an atmosphere, a thin sort of mixture of gases that really does do the Earth a service. It's what makes life possible on our planet, keeps the temperatures in that kind of Goldilocks zone for life, but it protects us from gamma rays, X-rays, the majority of the UV rays, so it does protect us, and it has this layer within our atmosphere pretty far up, maybe 30,000 feet in there, and in the stratosphere, known as ozone. So there's that ozone layer, and it will absorb, 30 kilometers up there. Most of that UV radiation, although some of that does get through, that's why you need to wear the sunscreen and your sunglasses to protect your eyes from cataracts. So we also have some water vapor up in there that will, absorb a lot of the infrared radiation. But we have what we call these little atmospheric windows, visual windows that some of that electromagnetic radiation does make its way through. We are thankful that the gamma and the X-rays and the majority of the UV does not get through, because those are the very high energy wavelengths, right? So they're short wavelengths carrying high energy that is lethal to us. So, but there is a little window here where it's called the visual window, where our visible light spectrum, so the violets clear to the reds, make its way through. So those particular wavelengths, okay, can get through. We say that the atmosphere is transparent, meaning it does go through to those wavelengths. Okay, so it's a little atmospheric window in the visual spectrum, and that's kind of why our eyes did evolve to be able to take advantage of visible light, because it is what makes its way through our atmosphere. So there's a little window in there that we could get some information on the visible light spectrum. And then there's also one here, as we're getting towards longer wavelengths, in the radio wave. And we definitely take advantage of radio waves with our telephone communication, that kind of thing. So, astronomically, they do take advantage of the radio waves, building the radio telescopes and such. So these little atmospheric windows are where our atmosphere is transparent to certain wavelengths. And thankfully it does block a majority of some of these very lethal wavelengths in there. So if we were to kind of want to study the gamma rays and the X-rays and maybe in there in the infrared waves, we need to build telescopes either way up high on a mountaintop at high altitudes where you're getting above the majority of the atmosphere. It does thin as you go up in altitude, or we just need to get these telescopes spaceborne, so out there in outer space to tap into some of these other wavelengths that we can't really get because our atmosphere blocks it. So a little atmospheric window in there. So okay. So building our optical telescopes here. The main thing that we want to do is to be able to focus the light into an image, okay? And so there's a couple ways that we build these. One uses a lens, okay? And it needs to be a flawless lens. And that's known as a refracting telescope, okay? Where it actually, as the light comes through, it will bend or refract and try to focus those waves into a focused image. Okay, so it's passing through the lens and it's trying to bring that into a focused image as best we can in there. So that's a refracting kind of a telescope. Okay, and then the other type is it uses a mirror. Okay, with some sort of a reflective surface on it that reflects the light. Okay, it comes in and it bounces back off and it reflects it and forms an image, so kind of bouncing off of the light. So that's a reflecting variety of telescope. Now we kind of have some advantages and disadvantages with these. But once again, the refracting telescope is going to use a lens as its primary objective and try to gather and focus by refracting or bending the light. The reflecting telescopes, its primary objective is a mirror, something with a reflective surface on it. We have an eyepiece that ends up being used for magnification. So we'll be looking at the three powers of a telescope, and magnification is one, just making the image larger if we can. And focal length then is the distance from either if you're using a lens or if you're using a mirror, okay? So the distance from that objective to the image it forms at a distant source, okay? So we've got the lens in this one, and we've got a mirror in this one. So this one would be the refracting, and this one would be the reflecting variety of telescopes. Okay, well, a problem that we have with the refracting variety of telescopes. So they will refract, but what's happening as the light is passing through, or just take for example the visible light, remember that kind of blue end of the spectrum, the shorter wavelengths, okay? Those are going to bend the most, okay? And then the longer wavelengths, the reds, bend the least. And so you get to where you've got these varying angles of refraction or bending of your wavelengths that the focus doesn't match up real well, okay? So the color kind of separation that happens then, kind of get this little blur around everything. It's called chromatic aberration. Chrome is color. Aberration. Really can't correct that 100% on that, but yeah, the shorter wavelengths are going to bend more. So think of, say, the blue end of the visible spectrum, and the longer wavelengths bend less, okay? So like a red wavelength. And you get this blur kind of around it, this chromatic aberration, they call that. That's sort of a disadvantage that's inherent with a refracting type of a telescope. So most of the telescopes, for several reasons here, the very large ones that we use for astronomy tend to be the reflecting variety because of that. And plus your lens can't have any flaws, whatsoever in that as well. So, yeah. Okay, yeah, it must be very pure and flawless because the light's got to be able to pass all the way through it. So it can be very expensive to make those. So a great advantage of the reflecting is it's not bending the light, right? It's just bouncing back, a reflecting one. So they don't have a problem with the chromatic aberration. So that's a good advantage for it. And the mirrors, of course, are less expensive to make. Again, they like to make the largest that they can possibly afford, They do have a budget, but the reflecting type are going to be the less expensive to be able to try to support, the weight of that. Yeah, the mirrors are the way you kind of are going to go. And probably the greatest ones, yeah, every large one that's been built since 1900s has been the reflecting type. A variety of telescopes. And then, of course, the radio telescopes. Here's a wonderful radio telescope here. And you can make those very large gathering area to get, but in the radio wave end of the spectrum. So those do make it through Earth's atmosphere, so we do have a radio wave atmospheric window, and so that's a good one to be able to get information. And so they do build those radio telescopes as well. So we want to look at the powers of a telescope, and there's 3 powers of the telescope that we're going to be interested in. Of course, probably the most important one is the light gathering power. So you want to build as large of that primary objective, so either the lens or the mirror, to be as large in diameter as you possibly can, because the area of that is what we're after. And the larger the area, the greater the light gathering power, so the ability of the telescope to collect light. But it is really based on the area of that lens or that mirror that you can get. So you really want to build those as large as they can, trying to increase that large gathering light power by making a large area, okay, in their lens, okay, or mirror, because mirror is cheaper. That's usually what they do in there. Okay, so it is proportional to the area. Okay, that's what's important. That's how we're getting greater light gathering power. The greater the area of your lens or your mirror, the greater the light gathering power. So they do make those really large telescope. That's why they want to make them so large, because that's what they're trying to do, is gather more light. Okay, that's one, the light gathering power. The second power of a telescope is called the resolving power. And this is the ability of the telescope to reveal the fine kind of details in there. And so a consequence of the wave-like nature of light is that there's this inevitable blurring that you get called a diffraction fringe around every point of light in your image, okay? So the resolving power is also dependent on the area of your lens or your mirror, if you're using that type. So again, diameter, or so area is that one. So you want to improve that resolving power, you need a very large diameter. And something that they'll do, which works really nicely, is to take several separate telescopes and link them up virtually and create, in that manner, create a larger area, okay, overall area. And we call that an interferometer. So there's that term, if you can see that on there, interferometer. So one way then to improve the resolving power is to connect 2 or more telescopes. Okay, so in this little picture, we've got, it looks like 3 separate telescopes, okay, that are receiving light, okay, and in essence, okay, virtually kind of simulated, creates this larger diameter telescope. And so those are called interferometers, a technique that's used to increase your light gathering power and your resolving power. So precision optical paths in those tunnels there. So the final image covers more area, so you're getting better light gathering power, better resolving power as well. So an interferometer, so like a virtual kind of telescope in that manner. Interferometers, yeah, were first done in the radio wave, so radio astronomy, taking dishes that are several kilometers apart and then sort of virtually bringing those together. So yeah, that's a good way to get that. Okay, high quality optics. We need the high quality optics as best you can get to help that potential resolving power. We do have one more power, but they're going to talk about these conditions that astronomers call seeing. So your best seeing conditions. You definitely want air that is calm. So this is the reason why they build these large telescopes way up high on mountaintops, where the air is not so turbulent, calmer, even drier conditions when you get way up high altitude, and the air is thinner up there. So as you go up in altitude, yes, the gases do become a little more diffuse, the air is thinner as you go up, and so it makes it a little more transparent, so you don't get all the wavering of the turbulent air. So that's kind of called seeing, so that kind of avoids that twinkling, you know, that we see of twinkling stars. It's the turbulence in the atmosphere. So you really do want to build your telescopes way up high on a mountaintop. That's kind of the preferred method there. So, okay, and sometimes, you know, yeah, so the best is up on a high mountaintop, air is thin, steady, calm, drier, more transparent, all of those things. But adding, you know, some adaptive optics to it, difficult, you know, to, you know, improve the performance of your telescope. So there are some things that we can add to the telescopes. But the magnification power, they don't say a whole lot about it other than it's just enlarging what you have. So this is not anything inherent in your telescope. Light gathering power, resolving power are all based on the diameter or the area of your lens or your mirror, okay? Magnification power is simply, you're changing out your eyepiece, basically. So it's not an inherent part of your property of your telescope. Okay, so I will have you do a calculation for magnification, and they don't go through all the details, so I'll write up a little bit about the magnifying power. So we had light gathering power we talked about. And resolving power. So these do have to do with the area, okay, of your, you know, your lens or objective. Or mirror. With those two. Okay, the bigger the better, as much as expensive as they can spend. The last one here, though, the magnifying power. See, I had a little drawing of that. So there is a little equation, and we'll try to give you those. Okay, so the focal length of the objective is FP, of the primary objective, okay? The focal length of that divided by the focal length of the eyepiece. So we can switch out the eyepiece and change up our magnification. So here's my little drawing I'm going to try to do for you. Here's my lens or my mirror, okay, and that's going to have the light coming in, right? It's going to gather the light and focus it, okay, to a little focus here. Focus. And then we can have a little eyepiece. I mean, you can change out your eyepiece to whatever, you know, and then you'll get your image up there. So this, okay, is the focal length of your primary lens, and this is the focal length of your eyepiece, right? So that's the eyepiece. And this is your primary objective, whichever you're choosing there. The lens or the mirror, either one. So that's our relationship here. So the focal length, so whatever that length is, okay, to the focus there, for your primary lens or mirror, divided by the focal length of the eyepiece, okay? And that'll give you your magnification. So really you just change out the eyepiece to change up your magnification. So let's say here we have a telescope and it has a focal length of 500 centimeters here of the primary lens. And I put in an eyepiece of 5 centimeters, so 5.0 centimeters for my eyepiece. So basically we'll plug that in, the focal length of the primary, okay, divided by the focal length of the eyepiece, 5.0, those are both centimeters. And what are you going to get? What do you get with that? You get a 100 times magnification. Right, so 500 divided by 5 is 100. So that's a 100 times magnification. So really, right here, our focal length of our primary objective, so our lens or our mirror, that's inherent, right? That's based on just how much money you could spend to get the largest diameter, the largest area. And then the little eyepiece then is what will change your magnification. So that's not an inherent property of your telescope, right? It's something you can just switch in and out. That's the magnifying power. So these were the 3 powers of a telescope, as it mentions up there, 3 powers of a telescope. Okay. The magnifying power. But those other 2 were due to whatever area you could get, right? So yeah, its primary focus is to try to gather as much light as we possibly could to make whatever faint light we're having to get our way and make it larger. We're trying to get as much of that to appear brighter. So the light gathering power and the resolving power are fundamental properties of your telescope, and they can't be altered because that was however much money you had to spend to get that largest area you could possibly get. But the magnifying power can be changed simply by changing out the little eyepiece in there. Okay. So those were the powers of the telescopes. So yeah, most of the major observatories that we do build, so these are observatories on Earth, optical and radio. So optical meaning either a lens or a mirror, and then radio, kind of tapping into the radio waves in there. Really, we need to try to avoid this light pollution. It's crazy how cities and towns really do, because of the light we produce, it makes it very difficult to see the light coming in from the universe. And to be able to study that, you really need to be out, away from the light pollution. And it's amazing when you actually do get to see a very dark sky and you look up. It's incredible the amount of stars, more stars that you can see just with your, naked eye in a really dark location. So it's amazing. So light pollution can kind of be a problem. So, and then radio astronomers also face a problem of analogous to light pollution, but we are noisy. I'm telling you, we ourselves are very noisy. We have a lot of radio communication, but there are some very weak signals that do come, from the cosmos that can get drowned out because we're just so noisy that we could, miss some of this. So yeah, the sound pollution or the radio wave pollution as well. So yeah, it'd be terrible if we missed out on something from the cosmos coming in just because we were so noisy, kind of thing going on. But yeah, so a lot of these, again, you're trying to build these on the mountains or way down in a valley, kind of for the radio type of telescopes. But we're trying to get either really high mountain, far away from civilization, but that's difficult to get it there. And these telescopes are huge. Like I said, there's a little person right here, and then this is the telescope. Some of these are really, really large. It's hard to get that up, say a mountainside kind of thing, and away from civilization, so it's not so noisy and there's not so much light pollution to deal with. But yeah, research telescopes are going to focus their lights to positions at which cameras and other instruments can be placed. So we're trying our best to find locations for them and put adaptive optics on them as well. Okay. Okay, small telescopes can use some different focal arrangements that the larger ones can't, kind of thing, so it might be inconvenient for larger ones. And so the Earth is rotating, right? We learned that the Earth is rotating, that it moves, it rotates and it orbits as well. So trying to keep our telescopes fixed on one place in the sky as we've got the rotating Earth going on. We've got to continuously try to keep the telescope positioned on that point. So on a celestial object that we're trying to study as the Earth is rotating on its axis or revolving as it goes in its orbit. So we call that sidereal tracking. It syncs it up to a particular object so that it's continuously staying on target, on position. So yeah, sidereal is kind of referring to the stars and kind of keeping a fixed point there. So they do have that to kind of keep them where we need them to be focused. And here we have just several different observatories that they talk about. So the European Southern Observatory has built the very large telescope. Some of these are not, such amazing names here. Astronomers, it's a very large telescope, and yes, it indeed is. So they abbreviate that the VLT, the Very Large Telescope. In the remote Andes Mountains of northern Chile, and so this has several. This variety is a reflecting telescope. It has 4 separate 8.2 meter optical mirrors, okay, that can function singly or combined as an interferometer. It could do that as well. So yeah, several of them, and you can combine them up or singly on these, but these are the reflecting variety, as you could imagine, because it's an 8.2 meter diameter. It's pretty large, very large indeed. Then this one here, this is built by an Italian and American astronomers, the Large Binocular Telescope. So LBT, Large Binocular Telescope, and it kind of looks like a pair of binoculars, but it has a pair of 8.4 meter mirrors. So again, a reflecting variety of telescope there. So the Large Binocular Telescope is another one. And then they're talking about one here on top of a volcanic peak in the Canary Islands. This one's got 10.4 meters in diameter lenses, so a much larger kind of a lens. Here we have 100 meters in diameter, okay, reflecting again with these. And I mean, they could use, some of them or, all of them, but we have 6 out of the 36 mirrors that are being used in this photo here. So they could use them as an interferometer as well. It's a great way to increase your area, right? Helping the light gathering and the resolving power. And so those varieties were reflecting telescopes. This one here is talking about a radio telescope in Arecibo, Puerto Rico. The world's kind of largest one that we have. And so, yeah, it's kind of sort of suspended in the air there. But yeah, again, very large diameters for these. The Very Large Array, so VLA, is one. It's very interesting. This is a radio telescope where it's actually got 27 separate dishes in this Y pattern, okay? And they use those, so they link those up as an interferometer so they can get a much larger area virtually with this. So that's a VLA. It has a great resolving power because of that. Very large, 22 miles in diameter for that. So linking them up as interferometers is very, very helpful. And those are radio telescopes. Let's see, the Square Kilometer Array is one that they are planning on building, and to the point that that would give you almost 4,000 miles, okay, which is a one square kilometer area that could give us. So that one, they're getting the work on that underway, the Square Kilometer Array. So a radio. Okay, so some optical and radio telescopes. And so now we want to add some things to it. So just looking through the telescope can't tell you really very much. It's being able to put some special instruments that we can attach to our telescope. And so they're going to talk about some of these, and we've got a whole variety here. Photographic plate, so taking, say, an image of the stars, and then you can look at the brightness of the stars on a photographic plate. There, photometers, again, trying to get the brightness of things, sensitive little light meters, charge couple devices, so CCDs. This is what we've got in our, like our cell phone cameras and different things like that. A much, less sophisticated one in our cameras. Array detectors are used like little photographic plates. So a lot of these things are added. You could even digitize, converted to some digital numerical data to digitized data. So save that as memory for later. So a lot of these little things adding to our telescopes. Okay. This one is where they reproduce this as a negative. So they take the picture and then reproduce it as a negative. That can give some faint parts to be made easier. So like in that image, you can't see all the little stars kind of down in within here. But if you do the negative of it, so some little techniques that they use where, the sky becomes white but the stars are dark now instead of vice versa. They use false color images. So as I mentioned that kind of before, where we're wanting to use the entire electromagnetic spectrum, but our eyes only see visible light. So gamma rays, X-rays, microwaves, and all those, we don't see those. So what they end up doing is converting these into what we call false coloring. So even like with radio waves, we can't see those. Like in our meteorology, so that's what they're using when they're trying to, show you images of, say, intensity of precipitation, and they have it all color-coded somewhat. So in this example, we've got some radio energy map here where false color-coded red means that we have the strongest radio waves. And then on this one, violet is the weakest. And so we can kind of make some sense out of that, even though we can't see radio waves, but when we false color them, we can sort of set up where the energy is greatest, where it's the weakest. So false coloring images is an important tool that we do use to enhance our telescopes. The spectrograph. So the spectrograph is like revolutionary in astronomy. It's almost as if astronomers say, we don't know anything about a celestial object until we see the spectrogram from that, the spectrum from the light from that. So a spectrograph, so to analyze light in a detail, we want to spread it out, okay, into its individual kind of wavelengths, like the visible light, so like the rainbow sort of thing, into a spectrum, they call that, and they use that spectrograph for that. So I've got a little example of a spectrograph. So basically it has a slit for where the light would come through, okay, and it has a sort of a grating in there, almost like a prism, that will be able to refract and bend the light out into its variety of colors. So if we think of the visible light spectrum, your shorter wavelengths, the violets and the blues, are going to bend the most, and then the reds down towards the other end of the spectrum are going to bend the least. And so you're going to get a spreading out, a spectrum of color using a spectrograph. So it's got these little diffraction gratings in them, that like a prism, right? So the reds bend the least, right? And then according to wavelength. And of course your blues and your violets are going to bend the most, spreading it out into a spectrum. So that's visible light, but this occurs with other forms of light as well. But it gets spread out. And I mentioned when we talked about Newton how he worked a lot with optics. And yeah, this is some of what he kind of understood. He actually bored a hole in his bedroom and then allowed a thin beam of sunlight to come through and placed a prism in front of it and saw the spectrum, all the colors in the visible light, in white light. So a little something Newton played around with as well. But yes, these spectrographs revolutionized astronomy. So it is going to separate out the light, as you can see there, as the light is going through a prism and into what we call that spectrum there, okay? Blues, that end, the violets and the blues are bending the most, refracting the most. Reds, the longer ones, bending the least. And so we've got this beautiful spectrum that we can look at. Okay, a grating, a diffraction grating they talk about, but it's a piece of glass with microscopic little parallel lines, so like you've got tons of little prisms in there. And so we do get sort of a little diffraction grating, and there's like a scale on here. I'm going to try to show you. I don't know how this is going to work out too well. I'm going to try to show you. I imaged it. We'll see if we can get this to work, but magnify that a little bit. Switch over real quick. So I tried to image. Let's go up a little bit. Where I put my camera inside here, and so I was looking at the little screen there. There is a little scale there that will tell you what the wavelengths are in nanometers on the scale there. So the different colors, so I don't know how well that's showing up for you there, but on this end are the reds, okay, and then the oranges and the yellow, and then the greens, and then the blues, and then the violets on that end. So according to their wavelengths, they will spread across. And so just because you're not here to actually look through that yourself, I tried to do a little video of that on my camera for you. I just still don't know how well that's going to turn out. But yes, so if you're in lab, we will be playing around with some of our spectrographs in a spectroscopy lab that we'll do. So yeah, so our observations that are ground-based telescopes are going to take advantage of those almost two pretty much atmospheric windows. The visible light window, where that light does make its way to Earth's surface so that we could tap into that, and the radio window, that part of the electromagnetic spectrum. And remember the other ones, the gamma rays, the lethal rays. Thankfully, our atmosphere blocks those, or life couldn't happen here on this planet. It'd be lethal to life. But if we want to take advantage of looking at those gamma rays and X-rays, we've got to get up above our atmosphere. Okay, it does us a beautiful service. It blocks, the ozone is blocking out the UV radiation way up there in the stratosphere, protecting us really. But yeah, so we take advantage here on Earth, okay, of the visual, so the visible light, and the radio light wavelengths. And for the others, we got to go airborne. We got to go airborne and way up high in near the stratosphere, above the troposphere where all the weather happens. Or let's go get into space for these, so the space observatories as well. Okay, so yeah, I was talking about all of that. Most of that rest of the spectrum does not make its way to Earth's surface. So we got to go up, we got to do balloons, that kind of thing, or aircraft to get way up in there. Let's see, I already mentioned all that. So here's the Mauna Kea in Hawaii, trying to go way up, 13,800 feet. So again, trying to get up way as high as we can, where the air is much thinner for viewing. There's some other ones that they talked about. The Kuiper Airborne Observatory, KAO. So this would be helping us with infrared telescope, going 40,000 feet up. Sophia, stratospheric, so the Stratosphere Observatory for infrared astronomy. So looking in the infrared with this. But there are some others that maybe you're familiar with. The Hubble Space Telescope, so now out in space. Hubble's still going strong. Hubble just had its like 30th year anniversary that it's been doing its thing. It does have visible light capabilities out there, but in a little infrared, I think, as well. But it's still going strong, and they feel like it's going to go on until 2030, 2040, probably, our Hubble telescope, but out in space. Another one, maybe you've heard of the Spitzer Space Telescope. I wonder if we got some pictures of these. Yeah, here. Okay, so that's the Hubble. Hubble's about the size of, say, a school bus, something like that, out there doing its thing, still going strong out there. This one's the Spitzer. You probably can't see that too well, but the Spitzer is infrared radiation. It actually had to have some coolants to chill its optics, and it ran out of coolant, so it's no longer giving us the infrared, but you know, it still can do some visible things. And it got retired in January of 2020, so it got retired, but it ran out of the coolant quite a while back, but it was still doing some things in the visible light arena. But yeah, it had to have a coolant to chill its optics. Let's see, the Chandra, I don't think it's on here, but the Chandra X-ray Observatory, that one does X-rays for us. So we can look at the X-ray portion of the electromagnetic spectrum with the Chandra X-ray. Let's see, and no, I think it might still be, let's see, 2019 celebrated its 20th year of exploring. So the Compton Gamma Ray. So we've got an observatory that does gamma rays now. This one got deorbited in 2000, but it mapped the entire sky in gamma rays. So we have that good information that that one gave us. But again, these were in space for that. Okay, and I think we might have, oh, and this one's new, the James Webb Telescope. It keeps getting its launch date kind of pushed back, but now I think it's set for October of 2020. Or is that right? Let me make sure. 2021. Yeah, it keeps getting pushed back because there's been some issues. I think its sun shield ripped or something when they were doing some testing. So, and it will be a very interesting one. It has a lot of infrared capabilities, visible light capabilities, and so that one's down the pike. They've got it created, it's just the testing before they actually do launch it. So it's coming, it's in the works. The James Webb Telescope, Space Telescope. Okay. Let's see. There's the Chandra X-ray I was talking about. Subramanian Chandrasekhar was his name. Is an American Indian, and he'll become important. We'll hear the Chandrasekhar name again when we talk about stars. So he really did help us with the kind of the theoretical branch in astronomy. But yeah, we've got his name that'll come up again. Let's see, yeah, and some others here that they talk about. But another interesting thing that they do is kind of combine these various types of telescopes. So the Hubble is like a visible light spectrum kind of thing. And if you add that to the information you can get from the Spitzer, which was in infrared, and make a composite out of it, the combination of it, it just gives you that much more information about this the beautiful little spiral galaxy, the same thing in each image, and then they make a composite out of it, kind of combine all manners of the wavelength that we can get from it, so enhances it, our understanding in that way. Okay. And so that's chapter 4, and definitely we are curious, and our quest of the universe and understanding it. So a very noble trait we have. So if you do have any questions, make sure you get with me. You do have the study guide with several bullets on it, and you do want to make sure that you can answer all of the bullets. If you have any questions, just give me a call or send me an email, or we'll have a meeting or something. So until next time, see ya.